Okay, looks like the recording's going. Okay, real quick before we get into the math, I just want to make sure everybody got the announcement. I don't know why I didn't think of this before, but this was easy to do, and I'm imagining it might be helpful for y'all. So anyway, long overdue, but I've created a version of the content syllabus in which I've reordered the entries. And so the idea is that this is now representative of exactly the order that I'm going to be going through the book section. So you see we did 1.6 first. It's listed first. And et cetera on down the line. Today you're going to notice, for example, that we're doing 3.1. So I've, again, inserted that where it's going to be chronologically appearing in the section. So anyway, y'all can go straight off of this. You don't even have to look at the course content syllabus, which I can't reorder because I can't impose reorderings on the other instructors, right? But anyway, this has all the same information, all the same exercises, so this should be your primary reference. Yes?
I'm not seeing that.
You might want to reload or clear your cache or something like that. Yeah, there you go. Yeah. Okay. All right. So everybody's seen that. All right. So we're going to move it along now with 3.1. Again, inserted kind of in the middle of Chapter 2 because this section contains some ideas that I find particularly useful and valuable when we're going through 2.5, which we're going to do in just a couple minutes. So, so we've talked about parametric curves previously, right? Parametric curves are curves in the target of what we call the parametrization. So the function that parametrizes the curve is the parametrization. So old news. Okay, and y'all remember this notation here, etc. Okay, so let's think about what would happen if you take the derivative matrix of this function. And no big deal, right? You've got a certain number of inputs, certain number of outputs. You take the appropriate derivatives and you put them in the appropriate places. Here's the thing, though. There is, in fact, only one input variable. So, in fact, they're not even partial derivatives. They're just regular old Calc 1 style derivatives. One input variable means one column. Again, as noted, there are just derivatives, just regular old derivatives. And so the derivative matrix is this right here. Okay. All right. So, all right, now let's take a different point of view on this. Let's again, in recognition of the fact that this is literally a single variable function. There's one input variable. We've got a single variable function. We already know how to take derivatives of single variable functions. We've got an old formula from way back when. Right? And in fact, if you take this formula and apply it to this vector valued, now let's to be fair, this is a vector valued function, right? It's got multiple outputs. But if you do this process to the vector values, what you're going to find is that every step in this entire process is done one coordinate at a time. Right? How do you subtract vectors? One coordinate at a time. How do you divide by scalars? One coordinate at a time. And then I'm going to claim, and again, we're not going to get into formalities in this course, but I claim limits are also done one coordinate at a time. I'm going to ask you to trust me on that. So, in fact, what we have here is a different interpretation of the derivative matrix. It's the same thing, right? It's literally, again, because the Calc 1 definition of a derivative is done one coordinate at a time, this is a take on the derivative matrix, and in particular, this vector that I get when I compute this derivative matrix. So, that noted, I can interpret the derivative matrix as a vector, and I can even show you geometrically how to interpret what that vector means. What does that look like on our parametric curve? And a lot of this is going to seem familiar. You've done parts of this before, certainly. Let's look at this difference x of t plus h minus x of t. Each one of these is a point on our parametric curve. And when you do the subtraction of x of t plus h minus, color choices, x of t, right, purple minus orange, you get it's not quite a tangent vector, but you get a secant vector, right? And then we can ask, well, what happens when I divide by h, right? Well, then you're going to get a vector that points in the same direction. This fraction points in the same direction, but with a different magnitude. Something like that. And then, let's see, how do we visualize taking a limit? Well, this gets a little weird. The purple point moves along the curve and gets closer and closer, so this green vector gets smaller and smaller, but I'm dividing by h, which is also getting smaller and smaller, right? So there's some question about what that magnitude is going to end up being in the limit. But the point then is that this dark blue vector, representing this fraction, I appeal to your geometric intuition, it's going to be along this, let's see here, this secant line that's going to be coming more and more toward a tangent line. And in the limit, geometric appeal, assuming nice functions and regularity and nothing weird's happening, in the limit it will be along the tangent line, and thus it will be what we call a tangent vector. Okay, so nice interpretation then. Cool fact. The derivative matrix, being as it is a vector, for which we use this very convenient notation, which comes from, in fact, the good old Calc 1 definition of a derivative, that vector points in the direction the curve is going. And now I'm again going to do some sweeping under the rug of formalities. If you look at the magnitude of this vector, formalities I don't want to worry about, but the magnitude of the numerator is literally the distance that you've moved. Okay, it's an approximation of the distance because you've actually moved along the curve. Again, let's not worry about that. So distance. And h, of course, as you'll notice, is the difference between these time instances that we're looking at. So this is literally distance divided by time, and that's speed. So what we have is this lovely interpretation that our derivative vector points in the direction of motion, and the magnitude is the speed. That is an old physics concept. A vector pointing in the direction that you're going, whose magnitude is your speed. That's velocity. That's the definition of velocity. So derivative of a parametric curve is the velocity. Lovely conclusion. Now, let's call this a fourth kind of calculus, right? We've previously talked about calculus of graphs, calculus of level sets, calculus of what I like to call the literal picture of functions, right? We interpret calculus differently in all those contexts. Here again, number 4, calculus of parametric curves. Different geometric interpretation from any of those other 3. And again, make sure that you classify this right in your mind. Make sure that you don't inadvertently conflate. Don't make this interpretation if the picture you're looking at is a graph, right? Catastrophe, crash and burn nonsense, garbage. Okay? So make sure to keep the different kinds of calculus separate in your minds. Okay. Okie dokie. So, and by the way, I'm going to point out while we're here, you've actually seen probably a version of this in a Calc 1 class. In a Calc 1 class, there's a standard example where they talk about this car that's driving along the road, and how far it's driven as a function of time, and you take the derivative and you get the velocity, and you take the antiderivative of the velocity and you get the position. So y'all have seen examples like that before. This is really the same thing, just kind of a multi-dimensional version of that same idea. Okay, So hopefully no surprise. Likewise, by the way, the derivative of velocity is acceleration. And so said differently, the second derivative of position is acceleration. All right. So let's see an example of this in action. Again, you're going to notice a lot of familiar sort of earmarks of this example because it's a lot like stuff you've seen already. Okay, so suppose we have some particle moving around in space and we don't know the position, but we do know the velocity as a function of time. And we do know the starting position, what we call an initial condition. Okay. So, all right. First question, what's the acceleration? Now, acceleration is the derivative of velocity from the previous page, right? So acceleration is the derivative of the velocity. Okay. So this turns into just a little bit of calculus, and I hope y'all are good with all your derivative rules. I'm going to, again, assume that y'all are strong with, derivatives of exponentials and polynomials and trig functions and logs and all of the chain rule, product rule, all of that stuff. You got to make sure you're good with, and there you go. This is what you get in that case. Second part of the question, what's the position? Now, again, we were given the velocity. We want to find the position. And so, again, we have, from the previous page, we have a pat concept there, and that is because velocity is the derivative of position. That means position is the antiderivative of velocity. Right? So, again, I take the velocity that I was given, take an antiderivative, and that gives you position. Everybody good? Now there's one little sticky point on this. I think I actually uttered the phrase, the antiderivative. That's not right. There's a lot of different antiderivatives. Right, that's why we have to put the plus c at the end. You all remember what they, I think, inappropriately call integration constant. I would rather call this the anti-differentiation constant. Integration and anti-differentiation are extremely closely connected, but they're not the same thing. Right, so I'm going to be a little bit, anyway, that's me being fussy, but for your consideration. So, yeah, sure, you can do the antiderivatives one coordinate at a time, and that part's easy. But, again, don't forget to say plus c. If you just assume that c is 0, as would be implicit if you didn't write it down in the first place, well, that's just inappropriate reasoning. It's invalid reasoning. It's not true. Okay, so here's the second mistake that a lot of students make. Surprisingly large number of students just assume that the anti-differentiation constant, I'm going to call it, must be the initial condition. That, too, is nonsense. Absolute nonsense. That gets propagated in high school calculus classes because they restrict themselves to such a narrow category of examples where kind of coincidentally, it happens to work out that way in this very narrow category of examples that they restrict themselves to. But that's not how reasoning works. You just can't do that. It's garbage. Right? So anyway, please don't make that mistake. Here's how we actually evaluate an anti-differentiation constant, which I'm going to now revert because everybody calls these integration constants, and I was brought up calling these integration constants, and I'm fighting against my own experience and, the culture, etc. So, okay, fine, integration constant. How do we find that? Well, we take this equation and we rewrite it in consideration of the initial time t equals 0. So if this equation is always true, then it's certainly true when t is equal to 0. And when t is equal to 0, That's what position is. Let's see here, to the color choices. This, you plug in t equals 0, that's what that is. We're just plugging in t equals 0. Right? And notice what we get then is an equation in which we can straight up solve for c. And you'll notice that the c that we solve for, right there, very importantly, and let me get rid of all of the distractions here, that c, very importantly, is absolutely not that initial condition. Everybody on board? Okay, so I make a big deal out of this because when I don't make a big deal out of it, I see lots of students making this mistake. When I do make a big deal out of it, I see very few students making this mistake. Still, though, not 0. So anyway, don't let this be you. Don't just recopy that. Bad answer, but worse, bad reasoning. Okay, how we doing? Is everybody happy with this example? All right. Okay. Let's see. One other thing I wanted to point out. I've already made this point, but one other observation I want to make is there is a tendency to look at this, and you see that it looks like an integral. Very important. It's not. It's an antiderivative. An integral is a Riemann sum, the value of which is a number. This is not a Riemann sum. There is no interval on which we're evaluating this, as would be required for an integral, aka a Riemann sum. And the result that this is not a number. It's a function. Right? So important distinctions, and I know in high school classes they tend to blur because who cares? We just kind of need to get a feel for it, and you'll get the vibe of when you plug what into where to get, answers or something. But not okay at this stage. So make sure to realize that is not an integral. And furthermore, not only is it not an integral, it's also not area under the curve. What curve, for one thing? What area? And why would it be? Right? This is just absolutely not what that is. So we will discuss later how multivariable integrals work and what they represent in which context. And side note, there's a bunch of different kinds of them that are interpreted in different contexts. So there will be a lot to say about that. But for the moment, certainly not what we're doing here. Okay. Everybody okay? Okay, lastly, and I've got this noted on the content syllabus, but there's a bunch of stuff later in section 3.1 on Kepler's work on planetary motion, which is very cool, and it's historical, and I mean, it's really cool stuff, but not fair game for this course. It's not what we're doing. It's a digression. However cool a digression it is, we don't have time, and so this is straight up not included in the course. You're not responsible for it, and for entertainment value, if you're curious, go ahead. But it's really not. It's a digression. You really don't need to worry about it. That said, in the parts of the chapter about Kepler's work, there are a couple of things that you do need to see. These are just a couple of theorems. They're highly believable, I think. They're basically a couple of product rules. They're not hard to prove. You could totally prove these yourself. It's a useful exercise. I encourage you to do that. And you should make sure to know these formulas. If you have a couple of vector-valued single variable functions and you dot them, the derivative of the dot product obeys a product rule. And likewise the cross product. So again, useful stuff to know. And you are responsible for this. This is part of the course. Okay, moving along. So we're going to go into the chain rule now. Now y'all remember the chain rule. The chain rule is a fundamental tool for computing single variable derivatives. That's nice. It is also a fundamental tool for computing multivariable derivatives, but kind of in a different way. And oh gosh, I was going to say in a more important way, but I don't know. It's just different. Okay. So anyway, I am going to give you a certain point of view on the single variable chain rule. I know that y'all know the single variable chain rule. I have no question about that. Let me rephrase that. I assume that y'all know the single variable chain rule. Make sure that you do. Certainly not the point of what I'm doing here. The point of what I'm doing here is to take a particular point of view on the single variable chain rule. You're going to find that I do that a lot in this course. I'm going to take something that I know you know, but I'm going to look at it in this very particular way because lots of multivariable calculus ideas come from taking a particular point of view that generalizes really nicely. Right? So here's that point of view. I'm going to start with a particular point of view on derivatives. And we've talked about this one before. A derivative, among many other interpretations you could take, is a relationship between input velocities and output velocities. Right? A derivative is what you multiply, it's what you do, let's keep it general, to input vectors to get output vectors. These could be differentials. Here I've got them written as velocities, whatever. Okay, so everybody remembers this point of view on derivative? Yeah? Everybody happy with that? Okay, so that's the point of view I want to use to take my narrow, careful point of view on the chain rule. So now let's consider, suppose we have a composition of two functions, and let's see, we'll start off by looking at how f takes an x velocity and turns it into a y velocity, or I should say df turns the input velocity of f into the output velocity of f. And then we can also, though, consider, just as well, if g takes y as its input and gives z as its output, I could likewise talk about what the derivative of g does. The derivative of g will turn, oh gosh, what the colors, I guess I'll use red. Derivative of g will turn its input velocity into its output velocity by multiplication by the derivative of g. Now there is a third derivative in this picture, and that is the composition. Right? I can think not about just the first function f or just the second function g. I can think about the composition where x is my input that goes into this function called g compose f, the output of which is then z. And in the same way that the derivative of f turns x prime into y prime, the derivative of g turns y prime into z prime, well, likewise, the derivative of the composition turns x prime into z prime. How are we doing on that? Everybody all right? Yep.
Is x prime like dx?
X prime is, I want to think of that as dx dt. Yeah, so think of these points, there we've got a point x, and we've got a point y, and a point z, and I'm going to imagine that they're moving with respect to time. I just find that the convenient way to think about it. Yeah. So again, taking a narrow point of view for maximum convenience. Yeah. Okay, all right, so now looking at all of this together, I'm going to first do a hand-waving sort of interpretation of what's happened here, and then I'm going to point to the algebra that gives the same point of view. If the way I turn green into blue is by multiplying by some factor, and if the way I turn blue into red is by multiplying by some factor, well, starting off with the green, I'm multiplying by a factor, then I'm multiplying by another factor. Altogether, I've multiplied by the product of those factors. right? I mean, this is not a deep point. If I give you some number, and then I say, okay, multiply it by 2, and now multiply that by 3, well, you've altogether you've multiplied by 2 times 3. You've multiplied by 6, right? I mean, this, again, no big deal. So that, in fact, is the chain rule. Now we can see this algebraically. Let me try to get this all on the screen. There we go. I can take this formula for y prime. Actually, let me color code that a little better. It's this formula for y prime. Plug it into there, right? Then this formula for z prime, again, taking that and plugging in here, turns that equation for z prime into this. That's just plugging in. There's no deep water. Just plugging that into there. But then don't forget as well, we have that up there. And so look, down here I have something times x prime gives you z prime. And then up here I have something times x prime equals z prime. Right? So let's see here, getting rid of the distractions. Comparing this equation with that equation tells me that this must equal to that. And that's our chain rule. So again, the chain rule, from this point of view, is just the innocent observation that factors multiply. That's it, right? That's all this is saying. Each one of these is a multiplicative factor, and doing 2 factors gives you the total factor. All right, so again, maybe not the point of view that you saw on the chain rule back in your Calc 1 classes, doesn't matter, but this is a very nice point of view on the chain rule, I think, at least for intuitive interpretations. And this argument that I've made generalizes very, very nicely, very naturally to a multivariable setting. So let's do that generalization now. And reminder, we started off by interpreting the derivative as what you multiply by input velocity to get output velocity. Okay, the multivariable version of that. Whoa. Get this to cooperate. There we go. The derivative is what we multiply by input velocities, multivariable perhaps, to get output velocities, multivariable also perhaps. The same statement. It's, a little bit different, but this is the same idea of an interpretation of what does a derivative do. A derivative turns input velocities into output velocities, just like we argued back here. The derivative turns input velocities. These happen to be real velocities, right? But it's what you do to input velocities to get output velocities. So, same idea. Just now vectors instead of scalars. And importantly, this now being a matrix, because matrices are what you multiply by vectors to get other vectors. Right? Okay. Alrighty. Looking back at what we did next, we looked at a composition of, again, these were Calc 1 kind of functions. We composed them to get a new Calc 1 kind of function. And then we made an argument about how, what you multiply here and what you multiply here, altogether you've multiplied by the product. And that's exactly what we're going to do here. Here, I have a composition of one vector-valued multivariable function composed with another vector-valued multivariable function, And altogether, I can look at what the derivatives do, and I can think about how, well, there's an x velocity, and as a result, there's a y velocity, and as a result, there is a z velocity. And I know that the derivative of f is what I multiply by green to get blue. And I know that the derivative of g is what I multiply by blue to get red. And so altogether, what have I done altogether in trying to turn x prime into z prime? Well, I multiplied by df, and then subsequently I multiplied by dg. Altogether, I have multiplied by the product df times dg. And again, if you prefer, if you'd like, you may. Let's see here. Let me give me a second to clean up my picture. You may think of this as, well, we have this formula for y prime that I plug into there. Notice how I've laid it out on the page to be as reminiscent as possible of what I did on the previous page. It's the exact same ideas, just a different setting. This formula then turns into this formula. And now I have two different formulas that relate x prime to z prime. There is, on the one hand, the fact that clearly the derivative of the composition is what does it. Then there's the fact that, as we just showed, the product of these individual derivatives also does it. In other words, you can think of this as one step done by the composition, or you can think of this as a sequence of two steps done by the individual functions. And the punchline is that the product of the derivatives is the derivative of the composition. How are we doing? Everybody's good? Okay. All right. So I think there's a lot of benefit to be gained. I'm a big fan of this point of view by, oh gosh, if I can get this to cooperate, looking at this page here. This is, my take on why the multivariable chain rule, what is and why does it work, the multivariable chain rule, and compare that to this page where we were talking about the single variable chain rule. And again, I think you'll find that these are highly analogous. And so whatever comfort and experience and convenience you find with this point of view, that is just directly analogous, right? Nice little stepping stone to helping you understand this totally equivalent take on the multivariable chain rule. And then just as a lingo point, you'll see down here for the single variable chain rule, I summarize by saying differentiation turns compositions into products. If I can get this to enlarge, there we go. Right, you can see right here, we have a derivative of a composition, and we are recognizing that it is a product of the individual derivatives. So differentiation turns compositions into products. And, well, same here. Differentiation turns compositions into products. Here we have the derivative of the composition, and here we have the product of individual derivatives. Is that satisfying? Everybody see the analogy, the very strong analogy here? Okay, last little quickie comment. Let's see here again with the when I drew this picture, you'll notice I'm going to criticize my picture here. I seem to have assumed with my drawing that there was a two-dimensional domain going to a two-dimensional target, aka next domain, right? So two-dimensional, two-dimensional, two-dimensional. Everything about my picture is two-dimensional. And there's a temptation to say, well, doesn't that mean that my result only works two-dimensional. But you'll also notice that there's nothing about this picture in which I made any actual use of the dimension, right? The fact that this was only two-dimensional never came up. Here, I tell you what, there you go. Now it's three-dimensional. The argument still works. Exact same argument. Right? So this actually does work for any combination of dimensions. It doesn't matter. 2, 3, 5, 7, whatever. All good. Okay, let's see an example. Okay, here we go. I tell you what, I'm going to make it big so we can see better, and then we'll scroll as needed. So I have a lot of setup in this question. Look how much setup there is here. This is just so I can define what's going on. What is it that I'm going to be asking questions about? So we start off by just noticing, look, I've got this function called f. It takes two input variables, x1 and x2. It spits out three output variables, y1, y2, y3. Then I've got this next function called g. It takes three variables in and spits three variables out. And further, notice what comes out of f is exactly what goes in to g. So implicitly, I'm composing these functions. We've got f, we've got g. We also have the composition g compose f. And g compose f, let's see here. G compose f, right there. x1 and x2 are the inputs. z1, z2, z3 are the outputs. Okay. And then I'm going to give you some data about these functions, f and g. These are the individual functions. We need to have certain information to be able to do what we're going to need to do for this example. So there's what you need. We'll see how it comes up momentarily. And here's the two questions. We're going to start off by asking what is the derivative of the composition. And then in a minute we'll come to the second part of the question. For the moment, let's not pay attention. There's a particular partial derivative we want to compute. We'll come back to that. Okay, so to the question, how do I compute the derivative of the composition? I'm going to go back here to this page where I derived the multivariable chain rule. Again, here it is. It's a statement about derivative matrices. And here we go. The derivative of a composition. Boom. Answer. It's the product of the two individual derivative matrices. So that's what we're going to base our work on. Gives us exactly what we want. There's one little asterisk that I want to point out. Little subtlety. Notice df is evaluated at the point A. Notice the derivative of the composition is evaluated at the point A. But notice that dg is not. dg is evaluated at the point f of A. So let me just address why that is. I claim it's because it has to. It's the only thing that makes sense. And here's why. Let's think about, again, real quick, what does df do? Well, df turns input velocities, into f, into output velocities for f. And it's evaluated at A because I'm assuming that the input velocity is a velocity of a point which, at the moment I'm interested in, is at the point A. So df is evaluated at A because, well, of course it is. That's where we are. That's where it is that I want to know what happens when I start moving with some input velocity. Okay. Now let's think about the composition. Oops. The composition turns these input velocities into those output velocities. And again, it's evaluated at the point A because, well, of course it is. Because that's where I am when I'm entertaining the question of, hey, what would happen if I start moving with some velocity? Okay, well, where is DG evaluated? DG, keep in mind, DG turns this velocity into that velocity. And notice, where am I when I want to talk about this velocity y prime? What's the point that I'm at? Am I over here? No. This function g has never heard of x or a, right? When you're interested in this velocity y prime, it's because you're here. It's because you're at this point. That point being f of a. That's the point where you're at when you want to know what happens when you do y prime. And so that is where dg has to be evaluated. Is that cool? Is everybody on board with that? All right. Okay, so with that in mind, when we write down the multivariable chain rule, and here you go, that's just a recopy from the previous page. As, of course, we must, the dg has to be evaluated at the point f of 1, 2. Not 1, 2. F of 1, 2. And with that in mind, I've got to look at the DG matrix that I have. Here's the DG matrix that I want. Here's the DG matrix that I have. I'm a little concerned at first glance that doesn't look like it's at the point that I need it to be, but it is. It is evaluated at the right point because we are given that f of 1, 2 is 3, 1, 0. So that's why we need to know, for this example to work, that's why I need to know this particular fact right there. Everybody on board? Okay. And everything else is downhill because, let's see here, I need to know df at 1, 2. There it is. Boom, given. Sweet. This chain rule is computing the derivative of the composition at 1, 2. Cool. That's what I wanted. Perfect. Right? No subtleties there. And so all I have to do then is, take the formulas that I have, or the values that I have for those given derivative matrices, and multiply them together, and boom, done. There's our derivative matrix for our composition. That is that. Pausing for questions. Everybody see what happened there? A little subtlety with the evaluation point. If I can be careful with that. Let me show you one other little subtlety. A lot of, oh gosh. If you're not careful, right? If you take a computational plug and chug approach to a problem like this, the easy mistake to make is to look at this and say, oh, okay, I multiply the two given matrices. I mean, strategically speaking, I need two matrices. The question gives us two matrices. What else could it be? Right? I mean, it kind of has to be. So there are those students who will say, oh, okay, well then I need to multiply this times this. And let me color code that a little bit better. They will multiply this by this. And the green one's on the left and the blue one's on the right. So I guess I'll put the green on the left and the blue on the right. But notice how it actually worked out. The blue has to be on the left and the green has to be on the right. There is a switcheroo in the order, and that's important. Matrix multiplication is not commutative, right? So you got to get that order right. Confession, I wrote the givens in the wrong order on purpose to just as a means of detecting who's being careful and applying the theorem as it should be, and who's playing fast and loose and not really thinking through the details. Yeah.
So are we just following the order that's on the left?
Mm-hmm.
Which is
Yep.
That, so we're
Yep.
not like flipping. We're
Yeah. No, that it's not that you always flip, it's that you always follow the rule. Yeah. And let's talk about where the rule came from, and there's some unfortunate realities in this. But this, again, came from this picture. And here's what's awkward. In the picture, the function that is on the left, its derivative matrix is on the right. And in the picture, the function that's on the right, its derivative matrix is on the left. So that's just, this is an unavoidable consequence of standard notational choices, which in retrospect are a little unfortunate. Right? It's just unfortunate that this is how it gets written down. But we write diagrams left to right. That's the world we live in. Well, that's American convention. Right? We compose functions kind of arguably backwards, because the one that acts first, unavoidably, because we write functions on the left, the one that acts first in effect, then, is on the right, not the left. It's on the left in the diagram. It's on the right in the compositions. So, again, this is deeply embedded in conventions and culture and standards and notations. And, yeah, I agree, it's unfortunate. I don't like it either. But you can't fight City Hall. This is the way it is, and this is what we're stuck with. So all I can say is heads up, and please do be careful. Okay. All right. So, next question. The second part of the question was to compute the partial derivative here. Partial of z3 with respect to x1. How are we going to compute the partial of z3 with respect to x1? If I can get this thing to cooperate. There we go. Well, keeping in mind the composition takes these inputs and gives those outputs. So this question is asking us for one of these specific partials of the z's with respect to the x's, namely one of the specific partials in this composition. So we're going to be looking for a particular element of this composition matrix. Okay. Which element? Well, it says Z3. Z3 is the third output variable. So we need to look in the third row of our matrix. So it's going to be somewhere in that third row. Also, we're looking for a partial with respect to x1. x1 is the first input variable. Input variables correspond to columns. So we're looking for one of the entries in this first column. And at this point, well, now I know exactly which entry I'm looking for. This partial derivative that I'm interested in is, it's the entry in the first column and third row, and that means I'm looking for that entry right there. And so our partial derivative in question is 3. Everybody happy? All right. Okay, so a couple of am I out of time? Pretty close to. I have a minute left. Okay. You know what? I'm sure I owe y'all a minute. Let's go ahead and draw the line right here, and see y'all on Friday. Have a good rest of your day.